Science will change when actually the population says, we don't believe you guys anymore. Great discoveries in science don't occur because we spend a lot of money chasing things that seem fanciful. They occur because some quiet scientist somewhere that everyone has ignored has been in the lab working, and that person made a discovery which led to new understanding.
In the 1990s, Dr. Robitaille set what is possibly the most important world record for nuclear magnetic resonance imaging. When they said the power required to use 8 Tesla magnets to improve cranial MRIs would pose a major electromagnetic risk to the patients, he showed that they were wrong, and he did so by exploiting some of the key mistakes physics has made over more than a century. His discovery is credited with saving tens to hundreds of thousands of lives, all because he refused to take the standard science for true. He hunted it down, found the mistakes in history, and so what do you do after you've changed your entire field and medical service forever? You see where else those mistakes you found have been applied in science, and it just so happens, nowhere has it been more instrumental to our current understanding than on the Sun. The same physics which, when corrected, saves lives by incredible numbers, has now been applied to our star.
You know, we're taught as children, well, the sun's a gaseous plasma, and we think, well, this is really a modern idea, you know, but actually it goes way, way back. The sun became a gas actually in 1864. You know, we say in the gas model, well, the sun doesn't have a surface. This is just an optical illusion. It's caused by a change in opacity that causes us to perceive a surface there that is not real. Of course, many observational astronomers at the time actually believed it did have a real surface. Warren de la Rue, Balfour Stewart, which for those who know me know that he's one of the people that I have really admired a lot, and Benjamin Lowry, they wrote a paper and they proposed that the continuous spectrum of the sun was consistent with a fully gaseous sphere. So as you know, the sun emits in white light, and they said, well, the gas can do that. And then Franklin and Lockyer, now Lockyer was the founder of the journal Nature, they wrote, the gaseous condition of the photosphere is quite consistent with the continuous spectrum. Now, of course, this was false. A gas cannot give us a continuous spectrum. But today, we still argue that the sun can give us a continuous spectrum even if it's a gas. And these ideas go back to 1865. Now, all our physical knowledge since that time has demonstrated that this is not possible. Yet, we still prevail in saying the sun can give us a continuous spectrum even though it's a gas. And how do we do that? The way that they do it is they say, well, look, we have inside the sun, we have a lot of atoms, and they're in different states of ionization. And through all the sum of many processes, all these processes that we're going to add together, they'll give us that continuous spectrum, like magic. But everywhere else in spectroscopy, and I'm a spectroscopist by training, if you have a certain type of spectrum, you have a distinct process that produced it. So we get an NMR line. So every spectroscopic process that occurs in nature has a specific thing that produces it. Now, graphite produces for us the continuous spectrum. Once you understand why graphite produces a continuous spectrum, then the sun will be bound by the same mechanism. And that will also be true for any other continuous spectrum that you get in nature. This is in 1927. The solar atmosphere is necessarily gaseous since the pressures prevailing are known to be very low at these temperatures, except perhaps the last, there he talks about the corona at 3000, are above the temperature of volatility of even the most refractory known materials, such as carbon and tungsten. Thus, the important conclusion is indicated that the solar atmosphere, with the possible exception of the outer reaches of the corona, no known substance can permanently exist except in the gaseous state. And of course, this is because we have critical temperatures, and it was known that the critical temperature of even hydrogen is extremely low. I think it's like 33 Kelvin. And of course, when these people wrote this, they didn't realize that metallic hydrogen would exist, and that will have a different critical temperature, and so it could be a liquid at much higher temperatures and pressures. So basically, these statements are completely out of date. But if you ask an astronomer, why is the sun a gas? Just ask them, why is the sun a gas? It's a very simple question. And they actually will not be able to answer the question except to say, well, it's too hot to be anything but a gas. If you get the sun wrong, you'll get all of astronomy wrong. So it's extremely important that we set the phase of the sun correctly. Accepting a new phase for the sun will lead to the collapse of modern astronomy. So if you say that the sun is a liquid, astronomy will collapse. Well, some people say, well, this is a terrible thing. But actually, I think it's good for our children. It will give them some work in the future. Each star type, stellar evolution, and galactic formation has to be revisited. A liquid sun would be essentially incompressible by definition. So that means stars cannot collapse into black holes at the end of their lives. Stars don't collapse. Big Bang cosmology will be confronted with limits to maximal densities. So if the sun can't collapse, how do the stars collapse? How do you get material into nothing? There's also a problem for Eddington's proof of general relativity, because remember, and the citation is there, for Eddington, the corona could be treated as a vacuum. He had to have it as a vacuum. So we have densities there of 10 to the minus 15 grams per centimeter cube, which is, believe me, a very, very powerful vacuum. So remember that the proof of general relativity is that during an eclipse, the light of distant stars as they crossed near the sun was bent, and this became the first great proof of general relativity. But the problem is, if there's actually density in the atmosphere of the sun, in the corona, you'll have diffraction. And so then you don't have a proof of general relativity. So this has consequences when you change the phase of the sun. It's much more than just changing how all the stars are. Now, I've wrote a paper, got carried away, 40 lines of evidence that the sun is condensed matter. But actually, there's only one proof that we need. And this proof we've had since the days of Langley, when he first measured the continuous spectrum of the sun. And as I mentioned before, in order to have a continuous spectrum like this, the sun must be condensed matter. You cannot get it from a gas, and I've treated this in detail in this paper, Stellar Opacity, the Achilles heel of the gaseous sun. So you cannot take a whole bunch of non-thermal processes, just random spectroscopic processes, take a large sum, and then create this spectrum at every layer inside the sun, and until finally you get it on the photosphere. That requires that whatever soup you're building changes constantly within the sun to have the right properties so that it can change the spectrum with temperature. It just doesn't work. So we have Rosalind mean opacities, which the solar physicists use to treat this problem, and it's just an excuse for not understanding a process. So you can't do it with a gas, and that's the critical point. So Planck commented on the solar spectrum years ago, and people don't, Planck has done a lot in science, and people, they quote scientists when they want, and they decide not to quote them when they don't like what they had to say. But here, Planck says something to the solar physicists of still today. He says, now the apparent temperature of the sun is obviously nothing but the temperature of the solar rays. Now he's talking about the continuous spectrum. Depending entirely on the nature of the rays, and hence a property of the rays and not of a property of the sun itself. So he's telling you, this is not a property of the sun here. Therefore, it would be not only more convenient, but also more correct to apply this notation directly, instead of speaking of a fictitious temperature of the sun, which can be made to have meaning only by the introduction of an assumption that does not hold in reality. So Planck knows that in order to get a valid temperature, you have to follow the laws of emission, and those laws require certain things. You can't have convection. You can't have conduction. Now, is there convection on the sun? Well, clearly there is. Carrington showed us that there was convection a long time ago, right? We see the sunspots going around. The sun has convection currents. So that forbids you from taking a temperature. So that's against the laws of emission. You have to have enclosure, thermal equilibrium with a rigid enclosure. The sun never meets that requirement. Now, I like this slide because this slide, for people who can't understand the continuous spectrum and all the physics of, how do you get a continuous spectrum and spectroscopy, and they're not interested in this, and it's all foreign to them. But this one is so easy, right? So if this is a flare, it's a Doppler image of a flare, so the white that you see here is a flare that's coming out of the surface of the sun. And as it breaks the surface of the sun, you see these ripples that are going out. Now, in the paper, they actually talked about this resembles ripples on a pond. Well, ripples on a pond are transverse waves, right? Now, you only get transverse waves in condensed matter. So once you have a transverse wave, gases can only sustain longitudinal waves. So this image is enough. A child can easily tell us the sun is not a gas once you see this image. So I was going to talk about Kirchhoff's law because actually you can't really understand the sun without dealing with the problem of Kirchhoff. It's important to remember that a proper understanding of black body radiation is important as it touches virtually all aspects of physics, from the study of condensed matter to the understanding of noise power and MRI, which got me into this mess in the first place, to fundamental astronomy, to setting the temperatures of the sun using thermal spectra. So it's extremely important. This law is old and it has huge implications in physics. But the problem is that the law is not valid. It has no experimental proof. When Kirchhoff wrote the paper, it was all theoretical. There was no theoretical proof of what he was, there was no experimental proof of what he was saying. But a law of physics can only come from experimental proof. Kirchhoff had none. Such proof doesn't exist today. But a further problem for physics is that the theoretical proofs are invalid. There are no theoretical proofs of Kirchhoff's law. So last year, along with Steve Crothers, we went over Planck's proof of Kirchhoff's law, and we discovered that to arrive at Kirchhoff's law, Max Planck inferred that the reflectivities of two arbitrary materials were equal. So if you look at his book, which is cited here below, his equation 40 is that the reflectivity of one arbitrary material is equal to the reflectivity of another. And that's a complete violation of all of known physics. The reason that we see colors is because reflectivities are not equal. They're never equal. The reflectivities of two arbitrary materials are never equal. So Planck could never properly arrive at this equation, but nobody caught him on it. This equation has been sitting in an important physics book for 100 years. Everyone can understand it, right? It's just A equals A prime. It's the same thing, or R equals R prime. These two reflectivities of two arbitrary materials are equal. Planck tells us the reflectivities of all arbitrary materials are equal. That's a violation of all of known physics. Now, in Planck's world, what does this mean? In Planck's world, there are no colors. So this is where physics has taken us to this date. Because of Kirchhoff's law, Planck's equation has never been linked to the physical world. It's a little complicated to understand, but every equation in physics has to be linked to an underlying mechanism. There has to be a physical cause. But Planck was never able to link his equation because, according to Kirchhoff, the means of generating the black body spectrum was independent of the nature of the walls. It didn't matter what the box was made out of. So Planck was never able to make a link. And this is a huge reason why astronomy is so messed up today. Planck's violation of the laws of reflectivity. And then also the fact that Kirchhoff tried to tell us that without experiment, that his law was valid. How do you make a law of physics without any experiments to prove it? In the end, Kirchhoff's law of thermal emission is not valid as it has no experimental or theoretical proof. As a result, the foundation of the gaseous sun collapses. And that's why I've spent so many years on Kirchhoff's law, people wondering why does he care so much about a law of 1859? And that's the reason, because now let's say, just look at your own lives. If there was a law that said, well, if you're British and you come and drive in the United States, you're not allowed to drive on the right. You must drive on the left. That would not be a good law, right? So the same thing here with Kirchhoff's law. What happens when a law of physics is not correct? And we have built all of modern physics upon it. That's a problem.